안녕하세요. 네, 저는 한국어로 하고 싶지만 그 정도 한국말 잘 못해서 제가 영어로 발표하겠습니다. My presentation today is looking at the impact of dust deposition on the South Atlantic and Southern Ocean, and looking at proxies for the impacts of ocean fertilization and phytoplankton growth. So obviously the mechanism through which this is important is the iron hypothesis, in which the iron which is contained in dust is deposited in these nutrient-limited areas of the Southern Ocean, which stimulates phytoplankton growth, which may then sequester carbon dioxide from the atmosphere and deposit it to the seafloor. I was particularly looking at the dust source areas in South America, so particularly in the southern part of Patagonia. And so from there you can see that the dust is emitted with the westerly winds, so it goes towards the east and into the Southern Ocean. You can also see that in that area to the southeast of South America, of Patagonia, that the area in this diagram, which is marked with orange and red colors, these are heavily high nutrient, low chlorophyll, so iron limited areas of the Southern Ocean. And so therefore we would expect that dust emissions coming from Patagonia could have an impact in removing the iron limitation in these areas of ocean. This diagram again shows in a little bit more detail. So we have that dust source in Patagonia. We have the rough limit, the northerly limit of the heavily high nutrient, low chlorophyll area of Southern Ocean. We traveled to South Georgia, so the subantarctic island, which is heavily glaciated, and we traveled there in order to retrieve an ice core so that we could look for dust deposition, but also the ocean primary productivity response. So this is a schematic showing the experimental design and the hypothesis behind it. So at point 1, we expect there dust emissions from Patagonia, and that dust could be entrained and transported directly to South Georgia at point 4 and deposited in the ice core. But along the way, we would also expect to see dust deposition into the Southern Ocean. So that's at point 2, where if there was iron deposited in the ocean, our hypothesis is that we would see a phytoplankton response. And some species of phytoplankton emit biogenic sulfur compound, so dimethyl sulfide, which is the only precursor to methyl sulfonic acid, and that would then be deposited also in ice cores in South Georgia. And so the methyl sulfonic acid could be used as a proxy for biological activity, phytoplankton blooms in the Southern Ocean, and we would look to see if that correlates with iron, which is contained in dust emissions from Patagonia. This is a high split plot which shows in the time period around just before when the core was collected. So we collected the core in October 2015. You can see over the previous couple of years, both in the southern hemisphere summer and winter, that the predominant wind the source area for wind which reaches South Georgia within 72 hours is predominantly to the west and in that area of southern Patagonia. This is just a satellite image which shows again that this area of the Southern Ocean does experience phytoplankton blooms also. And you can see those just to the east of the Falkland Islands there. And so we, as I said, we travelled to South Georgia and we skied up the glacier to our core site, which was at an altitude of about 1,000 meters on the plateau of South Georgia, a relatively stable area of ice where we hope to be able to get a good ice core. And so we extracted a 15-meter ice core, which was then measured and weighed and processed on top of the ice cap before being transported back to the laboratory for analysis. So this is some data from the ice core. So the top two graphs, so A and B. A shows the iron concentration in the ice core, and B shows the MSA, the methylsulfonic acid, concentration in the ice core. And you can see that there is some correlation between those two values. So we can see there does appear to be a relationship, which is a statistically significant relationship between iron concentrations and MSA concentrations in the core. We can also see in the graphs below, C, D, E, and F, these are proxies not in the core, but remotely sensed or measured proxies. And these proxies show the seasonal nature of the factors that also might affect chlorophyll concentrations. So C shows the chlorophyll concentrations in an area of the Southern Ocean upwind of the core site, and you can see that there appears to be a roughly seasonal nature where there are greater concentrations of chlorophyll in the Southern Hemisphere summer and lower concentrations in the Southern Hemisphere winter. We can also see the amount of radiation that the area receives in D. Again, it's seasonal. We can see sea surface temperatures in F, again seasonal, and temperatures at a monitoring station at King Edward Point, where there's a scientific base. Again, we see a seasonal temperature pattern. So in our core data in A and B, we were able to create an age model by matching the seasonal fluctuations in MSA to the seasonal fluctuations that we see in the other proxies, temperature proxies, and also chlorophyll concentrations. And we also, you'll see that our core record for iron and MSA finishes at a depth of about 6.5 meters. And, sorry, thank you, 6.5 meters. And this is because there appeared to be an unprecedented period of warmth, which was detected at the scientific station at King Edward Point, which caused soluble elements in the core to be dissolved and removed below this point. And so we trace that event to, in the record, to the 17th and 18th of February, and so we believe that is the bottom of our 6.5 meter core record, which we can use for alignment. You can also see there's a spike in iron and MSA concentrations at around July or August in 2015. And so we wanted to, this was the most strongly correlated area of the core, and so we wanted to see if we could identify a specific dust event that might have caused this. And we were able to find in satellite imagery and remote sensing of atmospheric particulate concentrations and also ocean chlorophyll, an event which was a dust emission from Patagonia on the 16th of August, which we could then trace across and passing south of South Georgia. And then a few days later, 3 to 4 days later, we saw an increase in the chlorophyll concentrations. And we know that phytoplankton usually responds on the order of 3 to 4 days after fertilization occurs. And so we believe that this event that we see in the record is this event which we can also track using remote sensing. So this is potentially important because of fluctuations in dust emissions from South America. And so we also retrieved a peat core from South America to look at how dust emissions might have changed over the past few hundred years. And so we retrieved a core from a peat bog in Tierra del Fuego. And this core allowed us to look back about 3,500 years. And during that 3,500 year record, we were able to see that at the top of the core, so in the past 180 years or so, that there has been a substantial increase, roughly a doubling or so of dust emissions detected in the core site in Patagonia over the past 180 years. And so from that actually roughly links in with some other research which I've done, which has found that since the Industrial Revolution, so since about 1750 or 1800, dust emissions around the world have roughly doubled as a result of anthropogenic activity and land disturbance. And so this finding is roughly in line with other global findings about increases in dust emissions. And so what this study showed was that not only is there appears to be a link, a statistically significant link between dust events and phytoplankton response in the Southern Ocean. So we can see that, I guess, that can be monitored on a continuous level and at an event scale. We know, as we saw, that the seasonal temperature changes and other seasonal factors tend to shape the overall chlorophyll concentrations, which are seen in the Southern Ocean at that time, but that these individual dust events do appear to have an important effect in triggering certain large-scale events. And so, as we also see an increase in dust emissions from southern Patagonia over the last 180 years, there's a chance that we would expect to have seen a greater productivity in the Southern Ocean in the post-industrial period. And so therefore, at the same time as we have been increasingly emitting carbon dioxide into the atmosphere, we have also, through dust emissions, been stimulating a mechanism to increase the withdrawal, the downtake of carbon dioxide from the atmosphere into the ocean through this phytoplankton activity. And so that has interesting implications for the future, depending on how we envisage or how we predict that dust emissions may increase or decrease in the future. Thank you.
감사합니다. 예, 제임스후퍼 회원님의 발표 감사드리고요. 혹시 질문 있으신가요?